Hi everyone, this is the first video for section 2.2 and 2.3, whole numbers and numeral systems. So I'm combining the worksheet for section 2.2 and 2.3 just because they go pretty well together, but like normal, this worksheet will have multiple videos, typically one per page of the worksheet. So let's get started. So on page 49, the first page of section 2.2, we talk about these properties of equality. So these may seem really elementary or really simple to you, but they're actually really important because these properties are why math works. So not every, as we'll see when we go through these, not every relationship in math has all of these really nice properties, but equality is one that does, and that's why things being equal just works out so nicely. So let's start going through them. So first off, we have the reflexive property. So that is the property that for any real number A is equal to itself, right? So this may seem really obvious, but all of these are going to have what we call counterexamples. So it's an example of when this property does not hold. So let's consider being a proper subset. So instead of looking at equality, we're going to look at being a proper subset. So in this case, X being a proper subset of itself, well, that's not true, right? X is not a proper subset of itself. X does not relate to itself in this way because by definition, being a proper subset discounts the idea of equality. So when we don't have equality, we don't have this reflexive property. So being a proper subset is not a relationship that has this reflexive property, but any number that we ever deal with is always going to be equal to itself, just because that's how this property works. Okay, so the next one is the symmetric property. So this one says that for any real numbers A and B, if A equals B, then B equals A, right? Again, this seems pretty obvious, right? A equals B. It doesn't matter what order you write these terms in, A and B. Equality works both ways, right? It's symmetric. You can flip the A and B, and there's this certain symmetry to this equality. So a counter example that we can have is less than or equal to. So we know that 3 is less than or equal to 4, but when we switch the 3 and the 4, suddenly this becomes false, but 4 is not less than or equal to 3. Right, so that's a counterexample of this one. So another counterexample would also be, right, a subset, because we have said that the subset symbol is really similar to this less than or equal to. So this is a counterexample of that one. So if we have inequalities, they are not symmetric because whenever you flip the numbers, or similarly when we have subsets and we flip the sets, this may not hold anymore. But this property is really good in particular because of you all being teachers. So you may have students. So for example, example 1 on page 49 has this problem: 7 plus x equals 3x minus 5. And we need to simplify that. So, right, once we add the 5 to both sides, we get 12 plus x equals 3x. So whenever you're teaching students this basic algebra, you may have students that insist that x has to go on the left side. But in this case, it may seem more natural to some people that, well, the 12 was already on the left, so may as well leave the 12 over there and move the x over. But you may have students that really truly insist that the x always goes on the left and that's the only proper way to do it. Whereas if you just continue to work this problem by moving the x to the right, oh, that shouldn't be 4, that should be 2 because we subtract x. We eventually get that 6 equals x, and it's okay that the x is on the other side, because if I give myself a little bit more room to write it, this is the exact same thing as x equals 6 because of this symmetric property of addition. So everything works out nicely. So if you ever have students who insist, you can tell them about this property and say, hey, it's the same thing because equality has this really nice property that we can use. The third property that we're going to talk about is the transitive property. So we've talked about this a little bit in section 2.1 that says for any real numbers, a, b, and c, if a equals b and b equals c, then a equals c, right? So a equals b equals c, we can just connect them like a chain, right? So a equals b, which equals c. We've also seen this with subsets, right? In section 2.1, we saw that E is a subset of F, and F is a subset of G. We can just combine them right along so that E is a subset of G. And likewise, it also works with this less than or equal to, where 3 is less than or equal to 4, 4 is less than or equal to 5, so that works right along. So I think the easiest counterexample to kind of get a hold of in this is one that actually doesn't use mathematical symbols, but instead uses words. So our counterexample is going to be, so really a food chain. So we have wolves eat deer. So wolves relate to deer by eating them. And now deer eat grass. So deer relate to grass by eating the grass. But we can't just put these together. Wolves eat the deer and deer eat the grass. That doesn't mean that wolves eat the grass, right? That's not how the food chain works. We don't have that wolves eat grass. Wolves are carnivores. They're meat eaters. So this is an example of, even though wolves eat deer and deer eat grass, this property isn't transitive, right? This relationship of being eaten and eating things does not have the transitive property. So I know, like I said, these properties seem really simple at first. We a lot of times just take them for granted in math because we're so used to math just working. But whenever you really get down to the foundations of why math works, a lot of it comes from, we have these really nice properties that math just has a lot of times. So I just wanted to really highlight these because they're essential to why we can do a lot of things algebraically that you just may not have thought of before. So this is the end of the first page, and that's all for this video.